In this session, we will discuss a laser beam in its characteristics. And you may think that you know it's a very straight emission. A laser beam is characterized by something which does not really change in divergence and in size. And we don't know anything about the distribution of the intensity perpendicular to the direction of propagation. After this session, you will have the answers to these questions. That's the purpose. To start with, I would like to introduce the two elements of the session. Number one is the definition and the deviation of the Gaussian beam. And number two is the propagation, the Rayleigh length, and the far-field behavior. We can derive what we call a Gaussian beam by many means. As a matter of fact, it is an eigen-solution of a resonator problem, which we can solve and find the Gaussian beam. But this is all too complicated, and in this session we will derive it from a very phenomenological point of conflict, as I will show you in a second. If you think of a planar wave, a plane wave, which we focus, then we learned in school that we will get a focal point. And this focal point theoretically has no size. It is focused to practically zero. Now, if we look at this consequently, we would have the fact that we start with a certain power in a beam and focus this laser beam, and what will happen in the focal point. Theoretically, the area of the beam, the cross-section of the beam, will go to zero, which then would mean that the intensity would go to infinity. So this theory definitely will not work for a real laser beam, because we know that a laser beam cannot have intensity infinity. To illustrate the real behavior of focusing a laser beam, we prepared a little experiment. So what you see here is a focal lens, and what we do is we have a laser beam which is just coming out of a laser, and you can see the beam distribution here. Now we send this laser beam through the lens and look what happens to the beam while we focus it. And on first sight, nothing really important happens, but if we go further down, of course, we see the focusing effect. So now the spot gets smaller and smaller and smaller, and now it should, well, what happens? It should go to zero. Doesn't go, no, it doesn't go to zero. It goes up again. So we have in the beginning a convergent part of the beam, then we have something like a minimum focus area, and then again a diverging phase further down the optical axis. So looking at the experiment, we now know that if we start with a laser beam which may not have zero divergence but have a more or less parallel behavior, and if we focus it, we observe experimentally it doesn't go to zero, so we do not violate this point of conflict of infinite intensity in the focus. And the reality shows that we have some type of smallest beam waste at some point, which actually of course is the point of the focal spot. There the beam waste has a minimum size. If we look in more detail and analyze some measured data of the experiment we just did, then you can measure this caustic, as we call it. So this behavior of converging and diverging laser beam radiation with a minimum size in the focal spot. And if you look at the right-hand side, you even can see the intensity distribution over that beam, and it looks like a typical bell-shaped size, a Gaussian distribution, and already you now see, you don't really know yet, but you see why we call it a Gaussian beam, because the intensity distribution over the direction perpendicular to the axis of propagation is a Gaussian beam profile. If we look in more detail at the propagation through this focal spot, you here see a moving intensity along the direction of propagation. This is extreme slow motion because what appears here in a second in fact happens in about maybe a femtosecond. So the scale of slow motion is about 10 to the 15. So this is real slow motion here. And if we look at the boundaries of that laser beam, we find this Gaussian beam profile with corresponding behaviors in the far field, more or less linear, and in the center we have parallel phase fronts, linear phase fronts, just for the reason of symmetry. If again we look at the distribution perpendicular to the direction of propagation, the intensity has this typical Gaussian beam profile, which scales as an exponential function of the dimension squared. If you look at the time average distribution of the intensity over the beam focus, you see the corresponding spot here. So we have highest intensity, of course, in the center of the beam, in the center by 2 means, in the focus, and in the middle of the distribution of the beam. Now, if we look at the corresponding quantitative description of these characteristics, the intensity is simply given by a Gaussian beam distribution. That is the typical exponential function r square over w. W is the beam waist squared. And if we look at the propagation of the beam waist in the direction of propagation, that's the second equation here, you can put in z equals 0, and then you just get w equals w0. So the beam waist at the center of the origin is just w0, and we have vertical beam propagation with respect to the phase fronts. And in the far field, at large values of z, we can neglect the 1 in the root, so we will have a proportionality of the beam waist with respect to the coordinate along the optical axis of propagation. So then we will have spherical waves in the far field. And a very important limit between the two cases, between the linear phase fronts and the radial spherical wave fronts, is called the Rayleigh length, ZR, the Rayleigh length, which is defined as pi w0 square over lambda. And if you look at it geometrically, it is exactly the crossover between the case of the linear behavior of the phase fronts and the spherical behavior of the phase fronts. And you can construct it, design it very easily by taking the parallel line of the minimum beam waist, drawing this parallel to the optical axis, and on the other hand, look at the crossover of this line with the limit of the far field divergence, which again is linear. And if you look at this crossover, this is exactly where the Rayleigh length is. And then you can see that the divergence angle theta is just w0 over ZR over the Rayleigh length. As a matter of fact, the tangents of that, but for small angles we can neglect the tangents. So this is the relation we will need later for further analysis. So again, the conflict was to have a change from more or less linear phase fronts to more or less radial phase fronts, and the solution is that we have a soft crossover of the two regimes. And how can we describe this? So if we look at the wave equation solution for a very simple form in a radial geometry, we know we can get these radial symmetric waves. Shown here is the solution, very simple. Here's the wave equation. Now we know this doesn't help, we need to add something. in order to introduce the description as a Gaussian beam, and this is shown here. It is called the slow varying envelope approximation. So again, if we start at the wave equation, but now don't use the ansatz of a radial wave, but use an ansatz where we have the product of a envelope u of x, y, and z and a classical exponential ansatz exponential to the ikz. Shown on the right hand side is what u really stands for. U is the envelope, the word for an envelope to close something is self-explaining, I guess. So we have the true oscillation of the wave, and we have an envelope which is just the connection of the maxima and the minima of that wave. And the slow varying envelope approximation now tells us that the change from one value of the envelope equation to the next value one wavelength later change is only very small compared to the value, the absolute value of this envelope part of the solution. So we have a slow varying envelope in respect to the values between two maxima of the wave. And mathematically, this is shown here. If we put in this ansatz in the equation and multiply it out, we get a factor where the deviation of the envelope with respect to z is neglected with respect to the value of the envelope itself. And this is called the paraxial wave equation. If we neglect this term, then we get this more simplified relation. And if we further work with this wave equation ansatz solution, we get the Gaussian beam, which is shown here. It's a little trick that we use to make the notification more simple, and that is we introduce a complex beam parameter q, which is just the product, the sum of the linear coordinate z and the complex part of the Rayleigh length. The meaning of the Rayleigh length, I think, is clear already as a limit, as a transition limit from the linear case to the radial case. So that is simply convenient and allows very easy mathematics. In fact, the consequence is that we can have the description of plane waves in this ansatz, in this solution, by the simple Gaussian distribution of intensity vertical to the axis of propagation, and in the limit of high z's, z large over the Rayleigh length, then we get the radial part of the solution. So this slow varying envelope solution is a combination which allows us to describe the linear phase fronts in the beam focus and simultaneously describe the radial behavior in the far field. So, to summarize this part, the Gaussian beam actually is a combination of a wave equation solution for linear phase fronts in the focus, and on the other hand of radial solutions of the phase fronts in the far field. And we have both integrated in one equation, in one solution. To get back to some more detailed characteristics of that solution, the slow varying envelope, here you can see the equation, the solution equation of the electrical field separated in a real and an imaginary part, in an amplitude factor and a phase factor. So, and as a consequence, we now can easily identify the relevant terms in this equation. You know already the beam waist behavior in terms of the dependence of the optical position along the optical axis, the behavior of the radii of the phase fronts we will discuss in a second. It's a very simple equation as well. And we have two expressions for the transverse phase and the longitudinal phase. So to get into more detail, you see here the behavior of the propagation along the optical axis z, and as expected, the relative distribution of the Gaussian shape of the beam does not change with propagation. It remains a Gaussian beam. However, of course, it gets larger in waist and more intense in the center, as you would expect. So the beam waist scales in the far field linear with the optical axis coordinate. And if we look at the divergence, we observe a similar behavior. The divergence, of course, in the beginning is 0 in this point of symmetry where we have the vertical phase fronts. In the far field, we have the far field angle theta in the limit. If we calculate this, it is just the ratio of the beam waist to the Rayleigh length. As you again can see in this design here, if you look at this triangle, then and you use the sinus law, then the ratio of beam waist to the Rayleigh length is just the tangents of this angle of the far field divergence. Now this is an illustration of what happens to the radii of the phase fronts. You remember maybe this formula here we had in the characteristics before. And if you look at the behavior of the radii of the wavefronts, this is the capital R value, it diverges at the point of symmetry because there the radius is infinite, because it's simply parallel, it's linear, and then it decreases and it comes to a minimum right at the point of the Rayleigh length. That's normalized here to the Rayleigh length, this coordinate, so at 1 z equals zr. So at the Rayleigh length we have a minimum beam waist, then the beam face front radius increases again with increasing z until the limit that it comes proportional to the coordinate itself. And for the beam waist we have this formula which we know already, also plotted here, and that decreases with decreasing z's, and with high values of z it simply scales linear as we discussed. So to summarize, this picture here shows again the overall behavior of a Gaussian beam, and now as a bridge to the next session on the resonators, you can see we draw in 2 mirrors, and the radii of these mirrors now match perfectly the corresponding radii of the phase fronts of the Gaussian beam at this position. So for one Gaussian beam we know exactly how to design it by putting mirrors with the corresponding curvatures at the corresponding places z, and then we will automatically filter this mode out of the infinite number of thinkable modes which could start in a laser. And as a little extra at the very end, of course you can design this resonator, this Gaussian beam, with such a configuration. However, I also could use a laser mirror with a little smaller radius at a different position. So this would give me exactly the same Gaussian beam, so I have different opportunities to select this mode by a corresponding resonator. So, to summarize, how do we describe a laser beam? Simple answer, with a Gaussian beam. Why? Because it combines the dilemma of infinite intensity in a focus with a limited beam waist, limited minimum beam waist, with a constant divergence behavior for high values along the axis of propagation.